Sì. Hey Tracy, how are you doing?
How are you?
Fine, how about you?
Okay, so we can start. Welcome to the third week. I'm Marco. My name is Marco Cirelli. I'm one of the other organizers. So if you need anything this week, refer to me or to Michele, who was around last week as well. And so this week is dedicated to cosmology, essentially, in the form of lectures by Tony Riotto and Tracy Baker. So let's start with Tony from University of Geneva, who's going to talk about inflation cosmology and cosmological perturbations.
Okay, thank you, Marco. So I hope you had a nice break, a nice weekend. So the course will be, as Marco said, about inflation and the theory of cosmological perturbations. So before starting, let me ask you, how many of you have not been exposed to a course of general relativity? Not been exposed. So only a handful number of people. Okay. All right. So the course will be, has basically one simple goal: to convince you that we have the capability of dealing with physics that has been happening around 10 to minus 35 seconds after the Big Bang, if there was a Big Bang, we're not sure. And to the fact that we are able to make predictions about this early epoch, and those predictions are in fact in good agreement with the data. Okay, so if you come out of this room at the end of the week with this message, I'll be satisfied. So the course, just a few news about the course. First of all, there is a set of lecture notes in the site. You can, you're more than welcome to download them and find errors or misprints or typos. Those, of course, are responsibility of my tutor, who is sitting there. There are also exercises that Matteo will take care of during the afternoon, if you're interested, of course. And some other important information. I will be using natural units. I guess most of the previous lectures have been using the same technique. So in principle, I will just set from now on C equal to 1, H bar equal to 1. Okay. And I will try to use energy units. So for instance, when I will be dealing with length scales, I'll be telling you that, for instance, 1 megapascal, which is a typical length scale in cosmology, is about, let's say, it's about 3 times 10 to the 24 centimeter, for instance. I know that 1 GeV to the minus 1 is of order of 10 to the minus 14 centimeter, and so on and so forth. So I'll be using GeV electron volts all the time. So you should be also be familiar with this to the way to go from one unit to the other. Okay. So in order to introduce the idea of cosmology in a general sense, and the idea of inflation in a more particular way, I will start with the Friedman-Robertson-Walker metric. Is it visible from the end of the room? Is that okay? Okay, so we know the universe is expanding right now. In fact, we know it's not only expanding, it's accelerating. That's the reason why we believe there is a cosmological constant or dark energy driving the evolution of the universe. But we are going to use, first of all, the famous cosmological principle. which states that the universe, if we look at the universe at sufficiently large scales, it looks homogeneous and isotropic. Okay? It simply means that if I take a point in the universe and I look at another point, which is maybe some megaparsecs away from it, the properties of this universe are the same, and also they are the same if I point my detector in one direction or the other. Of course, this is only true if I observe the universe at sufficiently large scales. For instance, in this room, of course, we cannot say that our universe, if we call this room a universe, is homogeneous and isotropic. So there is no very much agreement on the fact on which scales we should put a lower bound on to say that the universe is homogeneous and isotropic. Some people say 100 megaparsec, which corresponds more or less to a tenth of the size of the visible universe. We will come back to this point later on. Some people say that it's as much smaller scales and so on. But that's not important for us. We are going to assume from now on that the universe is homogeneous and isotropic. Okay? Mathematically speaking, it means that the metric that we are going to write down that describes the evolution of the universe has some Killing vectors, has some symmetries that are encoded in this metric, and these symmetries are of course rotation, because I want any direction to be equivalent, and the translation. Okay? So the Friedman-Robertson-Walker metric we are going to write is the following. Okay? I'm also using the convention minus plus plus plus. Of course, you might be familiar with the opposite, but of course it's exactly the same. Okay? So A of t is called the scale factor. It's a function of time only for the time being. We will promote it to be a function of the coordinates later on with some significance to it. But you see, this metric written in this way is very close to the Minkowski metric, with the only difference that the spatial part is multiplied by a scale factor, which is a function of time. This metric is of course invariant under translation if I send x into some x plus a constant, and also rotation, trivially. Okay? Of course, it does not preserve time translation, because the scale factor is a function of time. How many of you have seen this metric already? All of you. Okay? Very good. Now, if I specify this spatial part, we can write down in polar coordinates we can write down this dx square as dr squared divided by 1 minus k r squared plus r squared dt squared plus r squared, the sine square of theta, d phi square, where I've introduced a set of coordinates which are r, theta, and phi, which are the polar coordinates. How many of you have seen this metric already and they know what is the meaning of this parameter k, for instance? A lot. So I can go fast about this. May I or not? Let me just remind you that this parameter k to 0 or plus or minus 1, so you can set your coordinate system in such a way that you can always fix this parameter, it's not evolving with time, and has a given meaning. It sets the global geometry of my space. So this implies the global geometry of the space part of the metric. Okay, so if I ask some of you, what does it correspond k equal to plus 1? Can somebody answer me? Yeah, but what does it mean, closed? Closed doesn't mean anything. It's curvature of the sphere. Okay, so it looks like that you know very well what I'm talking about, so we'll go fast on it, which makes me happy. the only thing I would like to stress that this parameter fixes the global geometry. Okay, so meaning the geometry of the whole entire global universe, whatever that means. We will see, and that's the reason why I'm stressing this point, is that whatever is the evolution of my universe, this global geometry will not change. Inflation is this, we will see, is this violent expansion of the universe, can change only the local geometry, but it cannot change the global geometry. I will come back to this point, which is very important later on. Okay, for the time being, just stick to the point that this parameter k fixes the global geometry of my universe. It can be, therefore, a geometry of a sphere if k is equal to +1, where, for instance, if you draw a triangle, the sum of the internal angles is not equal to pi. It can be the geometry of an hyperboloid if k is equal to -1. So the sum of the internal angles of a triangle that you draw on this saddle is smaller than pi. And of course, it can be a flat geometry, k equals 0, the one that we learn in the elementary school, where in fact the sum of the internal angles of a triangle is equal to 180 degrees. Okay? So it seems to me that most of you already know all this stuff. So let me now directly jump to the question of who is setting the dynamics of this scale factor. Okay? So that is given by general relativity, because that is the interesting part of this metric. Oops. So the question is, if I want to describe the dynamics of this scale factor A of t, I have to write down Einstein equations. Okay, so I have to use basically a general relativity, and as you know very well, the Einstein equations are the following. Well, up to a couple of people in the audience. I'm sorry for those. Okay, so how many of you have seen already this equation? Very, very well. Okay, so that is Einstein equation. On the left-hand side, I have the geometry of my space-time. On the right-hand side, I have the energy-momentum tensor. Of course, I have to tell also what is the T mu nu. I have to satisfy the cosmological principle. The cosmological principle tells me that if I have a fluid, for instance, which is the assumption we are going to make, this fluid needs to be satisfying the properties of being rotationally invariant and also have the same properties whatever the point I'm looking at. So in particular, I'm going to choose from now on a T mu nu that is a matrix which is diagonal with energy density rho and three components which are the same, which are the pressure density. Okay? So again, rho is the energy density, P is the pressure density, and I'm going to assume that my universe, for simplicity, is only containing one typical fluid, okay, for the time being. Of course, this is not true all the time, but it's a good approximation for the time being, okay? So as you know from this generic equation, in fact, it's more than one equation, I can draw out of it several equations, which I'm going to write down, and those are the Friba-Robertson-Walker equations. So the first equation I can draw, if I define a parameter h, which is called the Hubble rate, and it's defined to be the derivative of the scale factor, so the dot here means the time derivative, divided by the scale factor a. Remember that the scale factor by itself has no physical meaning, so the only way it can enter in the equations is by ratios of scale factors. So if I define the Hubble rate, the first equation which I'm interested in is the following: h squared plus k divided by a squared is equal to 8 pi g Newton times rho divided by 3. Okay, this the first Friedman equation, which tells you how fast, if you like, the universe is expanding, even though it's not really correct what I'm saying, but it gives you the rate by which the scale factor is changing with time, and it's relating this rate with the content, with the energy content of the universe. Okay? The second equation that you can do, so this equation comes from the 0, component. If you combine the 0 and the ij component, you're going to get another equation, which is also equally important, which is the a double dot over a is equal to minus 4 divided by 3 pi g Newton times rho plus 3p. Okay? So in this equation, you have to notice the minus sign, first of all. It's going to be playing a crucial role in what I'm going to say for inflation, for instance. And is telling you how fast is the velocity, is the rate of change of the scale factor changing with time. Okay? Yes? Yeah. Oh yes, because this is giving you the curvature term. That is true, but it's if I have a physical quantity, it will enter in ratios. Okay. Okay. So plus, of course, I have to tell you an equation for the variation of the energy density or the pressure. So let me erase here. The equation for the energy density is the following: rho dot plus 3h times rho plus p is equal to 0. This equation, for those of you that are familiar with GR, comes from the covariant conservation of the T mu nu, the 0 component, one of the components, and is telling you how when the universe expands or contracts, the energy density changing with time, of course, in relation to the pressure. Okay? So some of you might know that this equation, in fact, in order to get it, you don't need general relativity. This equation is basically derivable if you take a Newtonian cosmology and you apply energy conservation. Some of you know this trick to find this equation in this way? Only one? So maybe it's a good idea to do it just for once. In any case, it is in the note. But let me tell you how it comes. So suppose you reduce yourself to the Newtonian case, Newtonian cosmology. What does it mean? It means simply that you have a non-relativistic fluid, something that is moving with a velocity which is not, of course, close to the velocity of light. And suppose that you have a region of your system which contains some energy density rho, and you take a sphere, okay, and you call the radius of the sphere, you call it A. Okay, so, and you put a particle, a test particle with mass m, on the surface of the sphere, okay, and then you let the system go. And you ask yourself, what is the radius of the sphere doing as a function of time? So what it's doing, you can trace it back to the energy conservation equation. Because what it's doing, suppose that it's moving with some velocity, so you write down that 1/2 the kinetic energy, 1/2 m times a dot square, minus the potential energy, which is g Newton times the mass of the test particle, times the mass m, which is contained in the sphere, divided by a. So m is going to be 4/3 pi rho a cube, is equal to a constant, which let me call it c, capital C. So I'm writing down that this is a constant. Okay? Now it's you see where I'm adding to, because of course if I now replace this m here by this relation, I have 1/2 m a dot square minus g Newton times 4/3 pi rho. Here I have a cube divided by a is a square is equal to a constant. Okay? Sorry, and then I forgot the m here. I have the small m. Now you divide everything by m. So you eliminate this m. You divide by m here. You also divide by a square. And you eliminate the a square here. Okay, and you have an a square here. You multiply by 2. This becomes an 8. Okay? And you see that if I call this thing, I call it minus k over a square, I get precisely the equation I wanted. Okay? If you use the second law of dynamics, you can also almost get this second equation, but you are not going to be able to find the pressure term here. Why? Because of course, in general relativity, you know that any form of energy will gravitate, and in general relativity, the pressure density is also a form of energy. But in Newtonian cosmology, you don't have it. So in that case, you will fail in obtaining this term here, but you get close enough. Okay? All right, so let's go back to this equation here, and let's see how far we can go. Yes?
So you said that the K before wanted to be plus or minus 1 or 2.
Yeah.
Does that mean that the total energy of a Newtonian system has only been?
No, it does not mean that. No, no, no. This analogy does not go that far. Okay. No. From this point of view, you can say that this K somehow, which has the meaning of telling you the global geometry of the universe, in this kind of analogy, gives you the constant energy that you have in your system. That's it. But so it can be positive, negative, or zero according to the initial conditions. But of course, you cannot just simply set from this argument that this parameter is. Well, I mean, to some extent, you can think you can do it because, of course, this constant you don't know. But it's in some units you can put it equal to 0, 1. Oh, that's clear. But as a physical meaning, I would say doesn't go that far. Okay, so now how about this equation? In the early universe, as we will see in a minute, the universe can contain different fluids. So we have 3 options that we discuss usually. First of all, we can have no relativistic matter, for which the pressure is basically 0. Okay. Then we can have relativistic matter, for which the pressure is equal to 1 energy density. The pressure density is 1/3 rho. And of course, you can have also the case in which P is equal to minus rho, and this is called the vacuum case. Okay, which in fact will be crucial for describing the period of inflation. Okay. So once you have these assumptions, you can solve this equation because you know now that rho goes how it goes as a function of the scale factor. Because remember that h is simply a dot over a. The equation, you can solve it very, very easily, and you can say that in the first case, in which p is equal to 0, this implies that rho goes like, so it's proportional to a to the minus 3. In the second case, in which P is equal to 1/3 rho, you can solve the equation and rho goes like a to the minus 4. Okay? And in the third case, in which P is equal to minus rho, then rho is a constant, does not dilute away as a function of. Okay? Now, why we have this kind of scaling? Of course, you can solve the equation, and but you can, of course, understand the physical meaning of this scaling, because if you have a non-relativistic fluid, think about a bunch of particles with a given mass m, let's say, let's simplify. You know that in this case, the energy density, you can say that is basically the mass of the particle, because if you use you can throw away the kinetic energy, for instance. So you can say that this goes like m over the volume, but the volume is scaling like 1 over a cube. So sorry, like a cube. So 1 over the volume is 1 over a cube. Okay, so this has to go like a to the minus 3, which in fact it does. In the case of radiation, of course you cannot use the same argument, but think about that. Suppose you have a bunch of photons. You know that the energy of the photons is h times nu, frequency of the given photon you're looking at, but the frequency goes like 1 over the wavelength. But if the universe is expanding, the wavelength is also stretched like the scale factor, and therefore you have something like this. Is very, of course, is very sloppy, but it will give you that this goes like 1 over a cube, which is a volume factor, divided by a, and therefore you get 1 over a to the 4. Okay? Because the energy of the photon, which is stretched, whose wavelength is stretched when the unit is expanding, is also the wavelength is going like a, so the frequency drops down like 1 over a. Okay? Okay, so those are the behavior, and once we have this behavior, then we can plug it in these equations. Can I erase here? I think. And we can have a look at the time behavior of the scale factor, finally, which is the final goal of writing the Einstein equation in the first place. So in the first case, you have that if you solve the Einstein equations, if you solve the equation that I just erased, you have factor goes like t to the power 2/3. In the second case, which is the relativistic case, a of t goes like t to the power 1/2. And in the third case, a goes like an exponential. So let me put some constant here, times t. How many of you have seen this behavior? Very, very well. Okay, good. So here I'm also going very fast because, of course, I have more interesting thing to tell you. Okay, so first of all, a couple of comments. This behavior as a function of time tells you that when you go back in time, since the equation, let me write it again. We are going to write it so many times, you'll get sick of it. So this is a equation that I will focus on. So this equation tells you that when I go back in time, if there was a moment where I can go back in time and the scale factor is very small, of course, I have to pick up the dominant piece here, the 1 over a to the 4. So back in time, the universe is radiation dominated, because 1 over a to the 4 wins over all possible power that I have in these three cases at least. When I go on with time, there will be a transition where the universe becomes matter dominated, because at some point the 1 over a cube will start dominating. And the moment at which this crossover is called the equality time. Matteo will have an exercise about that to compute exact details of this transition. And of course, there might be a period where the curvature term is also dominating at some point, because it goes like 1 over a square. In fact, it happens that that is not taking place, because we know that we are in fact now in a period where there is a cosmological constant or dark energy. So there is a period where the pressure in fact negative, and the universe is accelerating. But the most important point for me is the fact that when I go back in time, I will assume from now on that we are in a period of radiation. Okay, so all the particles are relativistic. I will assume, even though I will go back to this point, they will be in thermal equilibrium. So they will form a gas of relativistic particles. And from that assumption, I will discuss some problems that this old picture does have. Okay? Questions so far? Or curiosities? Or comments? Criticism? Nothing? Okay, very well. Of the particle horizon and the horizon. Okay, so I have an expanding universe, and intuitively you understand that if something is receding away from me with some speed, and I want to observe it, I do it by light, receiving light from this object, call it a galaxy for instance, or a cluster of galaxies and so on. A reasonable question to ask is, what is the maximum distance I can get in touch with in a causal way in my expanding universe? So if you like, what is the largest distances that I can probe using the fastest carriers I have at my disposal, which are photons? Okay? This maximum distance is called the particle horizon. So it's a notion of the horizon. So suppose that I have a my metric written in this way, and I want to write down the equation of motion of a photon which is propagating in this expanding or contracting universe. Of course, as you know, the equation is simply ds squared equal to 0. So I can say that the infinitesimal distance which my photon will propagate in a given time, dt, is equal to dx. Let's say I take the modulus of this thing, equal to dt over a. Of course, this is not my physical distance, because those are just co-moving coordinates. This x is a co-moving coordinates, is a fixed coordinates on my space-time. And if I want to compute the distance that a photon propagates from the beginning of times, let's say, to a given time t, what I have to do, I have to construct this quantity a of t times the integral between 0 and t of dt prime divided by a of t prime. Okay, so I take this object here. This is the co-moving distance, so I integrate from some 0, if there is a 0, to a given time t, and then I multiply by a of t because I want a physical quantity. Okay? So this is the maximal distance that a photon can propagate in a given time t. Okay? So let me erase here. And let's compute this quantity for a given power law expanding universe. So I will suppose from now on the a of t goes like t to the some power n, where we have seen that n is equal to 2/3. In a case in which I have a matter-dominated universe, it is equal to 1/2 if I have a radiation-dominated universe. Let's stick to these two cases first, okay? Which are the cases in which the universe is decelerating, because the acceleration is negative. Okay, so I can compute this object, and you see that this r a of t, it is what? It goes like, in fact, let me be more precise. We can say that we can fix the coordinates. So let's say that this is a0 times t over t0 to the power n. So let's be more precise. Okay? So here I put an equal instead of order of. So here I have a of t, so I rewrite this object here. And then I have times the integral between 0 and t in dt prime of what? Of 1 over this object here. So I have a0, and then here I have t prime divided by t0 to the power n. Okay? So this a0 goes away. The t0 also goes away. And then I have just the integral of 1 over t prime to the n, which is simply equal to 1 divided 1 minus n. And then I have the integral, which is t to the 1 minus n times t to the n, so I get simply t here. Okay? So I discovered that this horizon, so the distance that the photon is propagating for a given time t from the beginning of time, let's say, is proportional to t. Remember that I'm using a c equal 1 here. Okay, so I don't put a c. So that result makes a lot of sense, because of course it's telling you that in a given time t, if the velocity is equal to 1 in some units, then the photon is basically propagating for a distance which goes like t. Makes sense. Okay? But what is the most important information about this relation? The most important information is the fact that when I go back in time, this decreases. Not only that, but this quantity, if the lifetime of my observable universe is finite, this quantity is finite. Okay? So it means at any given time, during the expansion of the universe, my horizon, the maximum distance that I can probe sending photons around, is finite. Okay? So there are regions of the universe that I will not be able to observe if my universe has a given lifetime. Today, for instance, there are regions of the universe which we cannot probe simply because light did not have time enough to reach us, because the age of the universe is finite. Okay? That is the reason why when we talk about the universe, we always say our local universe. Okay? We have no idea how this universe looks like above the horizon. Most probably looks like the same, but we don't really know. Okay? So the horizon, the particle horizon, is finite in this sense for a universe which is decelerating, like when the universe is matter or radiation dominated. Another important thing that I can do using this equation is the following. I can rewrite in an elementary way this relation that I wrote in a different way. So the particle horizon, I write it as a of t times the integral from 0 to t in dt prime divided by a of t prime. Okay? And now I do the following. I write down the first time I write it. Now I change variables. I write down from 0 to a, and I write dt prime over dA prime times dA prime divided by a of t prime, let's say. Okay? I changed simply the integration coordinates. So from here I get a of t times the integral from 0 to a of dA prime divided by a prime. Okay, remember that divide by 1 over h so let's put a prime because I don't want to confuse with the coordinate t. Remember where in this passage I've been using the fact that h is equal to a dot over a. Okay? Yes. Because I'm supposing that, for simplicity, that I'm in radiation, and therefore there will be a point where A goes to 0 when at some point T star. Let's call it Big Bang, okay? Of course, I don't know. But in fact, we will see that for the inflationary cosmology, this is completely irrelevant. Yes, you can put it wherever you like. But my point is the following. In inflationary cosmology, the notion of the Big Bang is in fact physically irrelevant, so I don't really care about where I put it. Okay? My point that I would like to draw your attention on is that from this relation you see that the particle horizon is the integral of what? Of the logarithmic, let's rewrite this object as d, okay, is the integral of a quantity which is 1 over HA, which is called moving Hubble radius. So I want to introduce another notion which is called the Hubble radius. The Hubble radius is by definition h to the minus 1, which is a function of time, of course. Okay? The comoving Hubble radius is the same quantity divided by, so it's 1 over AH. Okay? Remember, every time you want a comoving quantity, you just take your physical length scale and you divide it by A. So you see from this relation, you see that the particle horizon is in fact the integral over the d log A of the comoving Hubble radius. So there is a very subtle difference between the particle horizon and the Hubble radius. The particle horizon is the distance that a photon can travel from the beginning to a given time t. The Hubble radius is the distance a photon travels at a given time t when the universe is basically expanding, when the scale factor is increasing by a factor of 2, let's say. Okay, so when d log A is over a unity, the universe is expanding all the time, and that is the distance traveled at a given time t by the photon, and the particle horizon is the integral of all the distances. Okay, from now on, we will use the notion of the Hubble radius all the time, and we will talk about the particle horizon less frequently. But the most important information that you also get from this equation is the fact that right now a distance can be smaller than the Hubble radius. Okay, so that this quantity here. But the particle horizon, in fact, it can be gigantic if the integral gets most of its contribution from the beginning of times. Okay, we will go back to this point later on. But the most important information right now is that from now on I will use the Hubble radius as the measure of the fact if a distance or a given wavelength or something is smaller or larger than the Hubble radius. Okay? So that is the notion of the particle horizon. Notice in particular that if I restrict myself to the case of matter-dominated or radiation-dominated universe, the Hubble radius and the particle horizon that I computed there are basically the same. Because if I say that a scale factor goes like t to the n, I know that a dot goes like n t to the n minus 1, and therefore a dot over a goes like n to divide by t, and therefore the Hubble radius goes like t. Okay? So you see, the notion of the particle horizon or the Hubble radius in a decelerating universe is basically the same, up to a coefficient. So we can talk about the Hubble radius, and we can call it the particle horizon because more or less you're doing a very small errors. Okay? But it's not always true. We will see that in inflationary cosmology, the particle horizon and the Hubble radius are completely different quantities. Okay? So please keep in mind the difference between the particle horizon, defined in this way, and the Hubble radius, defined in this way. Yes? Yeah, so the particle horizon is the distance that a photon can travel from 0, if there is a 0, to a given time t. The Hubble radius is the distance that the photon travels at the given time t, or better to say, when the scale factor of the universe is changing in logarithmic units by a factor of 2, let's say, or within a given Hubble time, which is h to the minus 1 in natural units, okay? And you see it, mathematically you see from here. One is the Hubble radius, the other one is the integral of it, okay? That is the reason why it's important to make a distinction between, of course, this quantity, the integral, can be large or small according to the fact that, how it behaves at small times, for instance. If there is some big contribution at small times, the particle horizon can be huge compared to the Hubble radius, and this is exactly what in inflation is taking place. Okay? Don't worry, we will come back to these issues later on. Okay. Other questions or curiosities? Okay. So far, so good. So now, next step is to discuss what are the shortcomings of all this picture. What are the problems? And I will do it gradually. First of all, I will discuss a problem which is called the fine-tuning problem or the flatness problem, that you can even say it's not really a problem. But then there is the horizon problem that I will discuss, which is related to this definition, that is in fact a physical problem. It's something that you cannot just disregard simply. So let me discuss first the flatness problem. Okay, so let's start from the usual equation, h squared plus k over a squared equal to 8 pi g Newton divided by 3 times rho. I can rewrite this equation in a different way. I can define some rho critical, which is simply 3h squared over 8 pi g Newton. Okay? And I can define, notice that this quantity is time dependent because the Hubble rate depends on time, and I can define a quantity omega, which is simply the energy density of my universe divided by rho critical. Okay, this is just a definition. Of course, it has a meaning in cosmology, but I don't want to go into very much detail. So if you use these definitions, you can rewrite the equation for the Hubble rate in a form which is maybe more interesting, which is the following. You divide by rho critical both sides and so on. This is a trivial passage, and you're going to get the equation omega minus 1 is equal to k divided by a squared h squared. Okay? This is an interesting equation because, of course, if you measure the Hubble rate, for instance, today, we know it's about 75 kilometers per megaparsec per second, blah, blah. So it's a number, you can measure it. If you measure a rho critical, therefore, because you measure h, if you measure by any means the energy density of my universe, I can take the ratio and I can compute omega. Okay, so something that you can measure on the left-hand side of this equation. Omega you measure. On the right-hand side, you see you have k, and k is the global, telling you something about the global geometry of the universe. So if I know what is the value of omega compared to 1, I can say, or I can think to be able to say that the universe will be closed, open, or flat. Okay? But we are not interested in this kind of discussion. We are interested in the behavior of this quantity as a function of time. Okay? Let's suppose that with today, omega minus 1 in absolute values is of order of unity. This is something that we know. Of course, this is a very, 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 very rough way of writing things. I could write down, the exact value with errors, but that's not the point. Okay, we know that omega minus 1 is of order of 1. Okay, that's enough for me. And then I want to go back in time and see what happens to this quantity here. Let's assume, as I said before, that we are only in radiation all the time. So I know that in this case, so I'm assuming a radiation-dominated universe, I know that back in time, the rho that goes like 1 over a to the 4 was dominating the behavior of the universe. So I know that h squared goes like a to the minus 4. Okay? Therefore, this omega minus 1 scales like 1 I have a squared here, here I have 1 a to the minus 4, so it's square when I go back in time. Okay? So this is a very rough, but gives you an idea where I'm aiming at. So from here, I can say that omega minus 1 in absolute value, let's say, at the given time t, divided by omega minus 1 at the given time t0, let's say the current time, goes like a squared of t divided by a squared of t0. Okay? Now, so far so good. Now I want to compute this ratio, selecting some time. To do it, I prefer to do it in terms of temperature, because radiation calls directly the notion of temperature, which is the average density, average energy of these photons that I'm supposing are present, or relativistic particles are present in my universe. And to do it, I need to tell how the scale factor at a given time, how I associated it to the temperature. How many of you knows this passage? Some of you, but no, only a few. Okay. So the way I do it is the following. There is nothing more isolated than the universe itself. So I can suppose that my universe is adiabatically expanding, and I can say that the total entropy of my universe, so this is a total entropy, okay, is conserved. So this is a conserved quantity. But what is the total entropy of my universe? It is the entropy density, S. So this is the entropy density. Okay, times the volume, which goes like a cube. Okay? But now, what is the entropy density of a bunch of relativistic particles? This is something that you learn during the university courses. If I have a bunch of particles that are in thermal equilibrium, I can say that the entropy density, suppose that they are bosons or fermions and so on, it goes like this. It goes like 2 pi square divided by 45 times g star. In fact, there is a label as here, times t cube. So suppose that you have a bunch of relativistic particles, might then be photons, neutrinos, electrons, and so on. They are in thermal equilibrium, they have a common temperature T, and you can say that the entropy density of your system is this times G star, which counts the number of degrees of freedom. Okay, it's not important for us for the time being. For instance, for the standard model, this number is 106.75. It's just a number of order 100 or so. The most important piece is the temperature here. Okay, so from this relation that S goes like temperature cube times A cube, and this is a constant, I draw the information that T goes like 1 over A. When the unit is expanding adiabatically, that's my assumption, the temperature of this relativistic fluid drops like 1 over A. Okay? This is not entirely true. There is also the G star, which also depends on the temperature, because some particles along the way, they become non-relativistic, they decay, and so on. G star is a function that depends on time, but for the level of accuracy we are using here, this is not really relevant. Okay? So I learned that T goes like 1 over A, but now I can replace, I can use, back to this relation, and I can use the fact that, therefore, I can say that omega minus 1 in absolute value at a given temperature T, let's say now, not time, divided by omega minus 1 when the photon temperature is about T0, goes like T0 divided by T to the square. Okay? Because I know that A goes like 1 over T. So right now the temperature of photons that we are receiving from the cosmic microwave ground radiation is T0 is of order of 10 to the minus 13 GeV, okay, 2.7 Kelvin. And here you see I can put any number I like. Let's be brave. Let's put M Planck, the largest energy scale you might think of, 10 to the 18 GeV. Let's say that T is of order of M Planck, which is the square root of 1 over G Newton, and it's about 10 to the 18 GeV. Okay? So 18 plus 10 is 28. Then I have 31. So this goes like 10 to the minus 62. Okay? What does it mean? It means that I observed today a omega parameter which is of order unity, okay? And in order to have it of order unity today, which if I stop anybody in the street and I ask anybody, what is the most common value you might think of omega minus 1, everybody will tell me 1. Nobody will tell me 10 to minus 64, correct? But the point is the following. If it is omega minus 1 today, back in time, it needed to be extremely small, and this is one example, extremely fine-tuned in such a way to have the value that it has today, the one that we observe. Extremely fine-tuned. You see? This is called the flatness problem because it means that omega during early epochs, in order to reproduce the value today, had to be extremely close to 1, up to a factor 10 to minus 62. But omega minus 1 is a flat universe. The universe that has a geometry which is Euclidean. So how is it possible the universe at early epochs was starting with a fine-tuned condition of being very, 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 very flat in order to reproduce the universe we have today? Okay? Look, this is just a problem of initial conditions. You can invent, you can propose a model of cosmology that will set the initial conditions to be this value. You can do it. So to that extent, this problem is not really, it's more a mathematical problem. If you're smart enough, you can come out with a universe that starts with these initial conditions. But of course, the solution must be somehow smarter than this. And inflation will do precisely this trick. Okay? Now, let me rephrase now this problem in another way, which will help us also to understand the solution to this problem. So I want to find again this number, or the same order of magnitude, but in another way. Okay? Which is useful to find the solution of the problem. And this is called, so it is the same problem, but sometimes it's called also the entropy problem. Okay? I want to tell you, I want to rephrase this problem to explain where is the physics, what is the real physical reason why these numbers are so small. Well, again, let's take omega minus 1 equal to k over a square h square. Okay? And this time what I do, instead of writing down the energy density of the universe, you know that h square, since I'm in radiation dominated universe, I write it as 8 pi g Newton divided by 3. And here, instead of rho, I write down the energy density of a gas of particles that will go like t to the 4th, as you know. So it is pi square over 30 g star, which is not exactly the same g star, but it doesn't matter for us, times t to the 4. Okay? This piece here is the familiar energy density of a gas of relativistic particles, which can be boson, either bosons or fermions, and the sum of these degrees of freedom is counted by this g star. Okay? But what is the important point? From here, I learned that the Hubble rate of my expansion of the universe is proportional to t squared, okay, eventually divided by m Planck. But that's not what I want. I want to rewrite this ratio as k divided by a squared. I replace here, I don't care about all these factors. We are dealing with small numbers, so I can throw away the pi's and so on. If you don't like this, put 2 pi equal 1 and call it a small circle approximation. It's okay. All right? So this goes like t to the 4. And here I have m Planck square. Remember that g Newton is 1 over m Planck square. Okay? So I'm arriving at this relation. Okay, so let me change the blackboard because otherwise it's messy. So let me rewrite it. I have omega minus 1 is equal to k divided by a squared t to the 4. So here I should put over rho because I'm forgetting the pi's and so on. And then m Planck square. Okay, now I do a crucial trivial passage. I rewrite this equation as k m Planck square divided by, notice the triviality, like this and like this. Okay? But now, what is the point of writing this relation? I know the entropy density, the total entropy, not entropy density, goes like T cube, A cube. Okay, so I can rewrite this as K, m Planck square, divided by S to the power 2/3, okay, times T square. Right? Okay, now is the non-trivial passage. The non-trivial passage is the fact that now you are supposing that the expansion is adiabatic. So this relation becomes equal to, and here I'm supposing adiabatic expansion, to say that the entropy is constant. So I write this relation as k m Planck square divided by S0 to the power 2/3 divided by t square. You see, I replace S, which is a function of, in principle, as a function of time, but I supposing that the expansion is adiabatic, and therefore I can put the present value here because it's constant. Correct? I can do it under these assumptions. Now let's take t equal to, let's evaluate this at t equal to m Planck because we did it before. So this becomes equal to k divided by S0 to the power 2/3. So what is the value of omega minus 1? Knowing that, assuming that, better to say that the entropy is constant, if I compute it at m Planck. Well, what is S0? S0 is what? Counts the number of photons that are in my observed universe today. Let's evaluate it. Okay, so it is T0, the temperature cube, okay, times the size of my universe, which we said before, computing the particle horizon, is T, which is 1 over the Hubble rate, and therefore this is H0 to the minus 3. Okay? Now we know that T0, we said, is about 10 to the minus 13 GeV. Okay? H0 in units of GV is 10 to the H0 to the minus 1 is 10 to the 42 GV. Okay? In more intuitive, it's about 10 to the 28 centimeter, if you want a big number, of course. But what is important here is that this S0 is 10 to the 90 if you put the numbers in. So our current universe contains, roughly speaking, 10 to the 90 photons. Huge number. Okay? Now take the power 2/3 and you get 10 to the minus 60. Okay? Which is close to the 62 that I was writing before. So this simple logic tells you that in fact the reason why there is a flatness problem, there is a problem of fine-tuning with this omega minus 1, is the fact that the universe contains a huge number of particles. Okay? While when you take the universe at the very, very beginning, when the temperature was in Planck, if you use this relation here, you see if I put T equal to m Planck here, since G Newton is 1 over m Planck square, the Hubble radius is order of m Planck. And there, what do you expect? You expect that your horizon contains at most one particle, not 10 to the 90 particles. But the universe, if I use this logic, must have born, so to speak, with 10 to the 90 particles in a simple horizon volume. You see? Phrasing the problem in this way tells you also the solution. Where is the critical point that I assume to get these numbers? It's here. The solution of the problem will rely on the fact that I will have to impose that during the evolution of the universe, there must be a period where this assumption breaks down. Okay? And in fact, we will see that inflation, or better to say the transition from inflation to the radiation phase, will do exactly what is required to break this assumption here. Okay? Is that clear? The reason why we are dealing with this, yes. Mm-hmm. Mm-hmm. Yeah. Yeah. Well, that will affect also this quantity here. Right? In the same way. To some extent, you are saying that, something can happen beyond the horizon. Yes. There might be elephants there, I don't know. But I don't know. I'm restricting myself to what I can observe. So based on what I can observe, this is the problem. Here, you mean, in this thing? Yeah, but again, it goes back to the question. I don't know what that is. I can only evaluate, I can only make this estimate using my observable universe. Right? That is the assumption I can make. Yeah, but what it is? Okay, good. I will give you it as an exercise this afternoon. What is the total entropy of the universe? Meaning what? The universe that you don't observe? You know nothing about? It's a very reasonable question. I'm not criticizing your question. It's a very good question. The point is that it's a meaningless question, in the sense that it is based on something that I can observe. Of course, if you have a full theory that describes whatever happening, then it might be reasonable. Yes, I agree. But these estimates are based on what I observe. Yeah. Yes. Yeah. This is what I'm assuming. Yeah. So I hope I was making very clear what were the assumptions that we make to get to this problem. Okay, so let me discuss the third problem, which is so these problems are somehow, as I said, the problem of fine-tuning, which, as some of the questions already tried to tell us, it might be a problem that goes away if you have a full theory that is able to explain the initial conditions, what is outside our observed universe, and so on and so forth. But there is another problem which is more serious, which is called the horizon problem, which in fact is related to the quantity that I introduced before. That is a physical problem in the sense that it is not something that you can solve so easily. So and this is the last thing I would like to do. And so this is called the horizon problem. Okay, so let's draw a simple picture that I will draw from now on many times, where here on the vertical axis I put a logarithm of a given length. Okay, and here on the horizontal axis I put the log of A. Okay? Let's draw the Hubble radius. The Hubble radius is a line, because remember that the Hubble radius is, since we know that h squared goes like rho, and we said that we can have 1 over a cube, or 1 over 8 to the fourth, if I have a matter-dominated universe or radiation-dominated universe. Okay? So from here, I get that h to the minus 1. So for a matter-dominated, I have to take the inverse and the square root, so it goes like a to the 3/2. And here it goes like a square. Okay? So here I take the log, so I have a given line where the steepness is dictated by the coefficients 3/2 or 2. Okay, I take the log. It's given by, so for instance, for matter dominated, I have 3/2 times the log of A. On the other side, suppose that I take a given distance. Suppose that I take the distance between you and the second row of this room. Okay? This distance in an expanding universe goes like the scale factor. So when I take the log, it goes like the log of A. So it goes like this. Okay? So this goes like log of A. So this is basically some distance. Let me call it lambda, a wavelength, let's say. And this is h to the minus 1. Okay? And suppose that we start from a distance today that is smaller than our Hubble radius, because I can see you, right? So photons have time enough to go from you to me. So I put my distance, which I draw by dashed line, to be smaller than the Hubble radius today. What is the problem? The problem is that when I go back in time, since the steepness of these two lines is different, sooner or later, suppose that we rewind the movie, and suppose that we take this room, we contract it because we want to go back in time. Sooner or later, the distance between you and me will go above the Hubble radius. So I won't be able to see you anymore. This is the problem. Well, it's not the problem so far, but this is what is happening. Is it clear? Okay? This is if I assume a standard cosmological expansion dictated by a radiation or a matter-dominated period. Okay? Now, what is the problem with this thing? The problem with this thing is the following. We receive, so let me say in words and then I will elaborate a little bit. We receive photons from of the cosmic microwave background radiation from all over the places. these photons have a temperature, which I said before is about 10 to minus 13 GeV, 2.7 Kelvin, which I received from all possible directions. Okay, from there, behind my back, everywhere. Okay? Those photons have right now a given wavelength, and they are coming from all over the places. And it is an experimental fact that whatever direction I choose to measure the temperature of these photons, the temperature is basically the same. It's 2.7 Kelvin, up to very, very small fluctuations of order of 10 to minus 5, 10 to minus 6, which will be the subject of the second part of the lectures. Okay, but so far let's focus on the average value. Let's forget about the small fluctuations. Now, these photons, of course, have a given history, and we can say that these photons have been generated or were born at what we call the last scattering surface. So let me elaborate a little bit about this. How many of you have been hearing about the last scattering surface? Okay, some of you, good, very well. So let's suppose that our universe is full of photons, and there are protons and electrons around. Okay? So during the evolution of the universe, these photons are able to scatter around, of course, and there are processes which are of the form a proton that meets an electron and form or goes back to a hydrogen atom plus a photon. Okay? We know that photons interact only with charged particles. Therefore, if during the evolution of the universe there is an epoch where it is more favorable from the energetic point of view to form hydrogen instead of destroying the hydrogen, from that point on, photons will not interact with the matter around because the matter will be formed by hydrogen. Of course, I'm extremizing the argument, but this is the logic. So during the evolution of the universe, at the beginning, the particles are not in the form of hydrogen. There are protons, quarks, and so on. The universe is cooling off. At some point, it becomes more energetically favorable to form hydrogen atoms from the protons and electrons which are around. And this is called the recombination epoch. And it is basically confused with what is called the last scattering epoch. Okay, that means that the last moment where the photons were able to scatter with matter, because there were charged particles around. When does it happen? You know that the first level of the hydrogen atom is 13.6 electron volts. So you might say, well, when the photon energy is about the same value, if it drops down that value, I will start forming hydrogen atoms. This is a very good guess as a starter, but in fact it's not a correct one. Why? Because if you make a computation, there are 10 to the 10 photons per baryon, per proton if you like. So it is, of course, you try to form an hydrogen atoms, but this is surrounded by 10 to the 10 photons. And if, of course, they are the energy is distributing with a given tail, there will be always photons able to destroy the atom. So you have to wait a little bit more for the temperature to drop down, and this is of order of, so let me put last scattering, is of order of 0.3 eV, okay, very roughly speaking. So it's a factor of 10 smaller than what you might expect it. Again, because the universe is overpopulated by photons. At this temperature, you form hydrogen atoms. The photons are not able to destroy anymore. So basically, what happens is that you go only in this direction. And this is called the last scattering surface. From that point on, the photons will propagate to us almost freely. The universe will be transparent to them. Okay? This is called the last scattering surface. Okay? So the last scattering surface is something that is surrounding us. And we get photons from when they were emitted at this point from all over the places. So you have a big sphere, let's say, which is the last scattering surface. Okay, and we are receiving photons that will come to us. Here is us, okay? So from all over the places, okay? What is the problem? The problem is the following, that these photons have the same temperature. This is what we observe. Okay, so the temperature here is this photon that comes from this direction as temperature T0, this is T0, this is T0. Okay? The problem is the following, that when you go back in time, suppose that you identify now this quantity here as the distance between this photon and these photons when they were emitted. Okay? Today we observe them, so we collect them in this room. They have a distance which is more than the Hubble radius, so they are in causal contact. But when I go back in time, suppose this is the distance between them. So this is my lambda here in this plot. When I go back in time, suppose that the last scattering surface is here. You can make a computation, that we are going to do it now, and you discover that their distance was larger than the Hubble radius at that time. So these photons, this one and that one, when they were emitted, were separated by a distance larger than the Hubble radius at that time. They were not in causal contact. There was no way, in principle, they could have talked to each other and tell themselves, we have the same temperature. Okay? This is the so-called horizon problem. The horizon problem is the observational fact that we measure photons coming from all over the directions, that when they were emitted, they were emitted from the last scattering surface. We measure them at distances which are larger than the distance, when you go back in time, of the causal horizon at that time. Okay, is that clear? This is a very important fact. So right now, what I want to do is to quantify this statement. I want to show you that in fact we have a problem. Okay, we want to quantify this picture here, and I will do it, and then I will stop, of course, because we didn't even take a break. So I guess you're tired. No, it's much larger. This is the temperature during the evolution of the universe when the photons for the last time scatter around. Then they propagate, the temperature is dropping down like 1/A, and today is 10 to minus 4 eV or something. So it's a factor 10 to the 3 smaller, more or less. Okay? So the computation I want to conclude this lecture on is to compute what's the typical Hubble radius at the last scattering surface. Okay, and I want to compare it to our universe today when I go back in time. Okay, I want to find how many Hubble volumes there were on the last scattering surface, and if this number is larger than 1, the horizon problem is there. Okay, is that clear? So what I want to do, I want to compute, first of all, I take my universe, which is h0 to the minus 1, and I want to go back to the last scattering surface. I want to take this room, which is our universe, shrink it, and I want to see how big was it at the last scattering surface. Well, that's easy. I just simply take my observed universe and I multiply by the scale factor last scattering divided by the scale factor today. I just shrink it. Okay? I want to compare this number to the horizon, to the Hubble radius at the last scattering surface. So I want to compare this number versus h last scattering to the minus 1. But on the other side, I know that h squared, we said, in fact, let's now suppose that the universe, I do the rescaling supposing the universe is matter dominated, because from now back to the last scattering surface, which coincides more or less with the equivalence time, it is matter dominated. So this guy goes like a to the minus 3. So h goes like a to the minus 3/2, and therefore h to the minus 1 goes like a to the 3/2. Okay? So h minus 1 last scattering is equal to h0 to the minus 1, properly rescaled, which is a last scattering divided by a0 to the power 3/2. Okay? This is the Hubble radius at the last scattering time. Okay, you just simply take the scaling and you go back in time. And you see now that if I take the ratio between this quantity 1 and this quantity 2, okay, the ratio, if I take now the ratio, this quantity here, and in fact I want to take the cube, because well, let's take the ratio. So the ratio is going to be h0 to the minus 1, A last scattering, divided by a0, divided by h0 to the minus 1, that goes away, okay, divided by a last scattering, divided by a0 to the power 3/2. So from here, what I learned is that this is simply, what it is simply a last scattering divided by a0 to the power minus 1/2, okay? So it is a0 divided by a last scattering to the power 1/2. And therefore, if you put the numbers, because this goes like the t last scattering divided by t0 to the power 1/2. I told you that t last scattering is 0.3 eV. T0 is 10 to the minus 14 GeV. So if you take the ratio, you take the square root. These numbers, it's of order of 10 to the 2. Okay? So if you take the volume, it's going to be 10 to the 6. So what happens is the following. There were 10 to the 6 Hubble volumes here on the last scattering surface. Okay, so there were basically 10 to the 6, about 1 million regions that were not connected causally, one from the other one. Okay? If I have 10 to the 6 disconnected regions, I have a very large probability to find a photon that comes from here, a photon that comes from here. So this region here was not in contact with this region here. There was no way they talked to each other, and in spite of that, we measure them today, and they have the same temperature. Okay? This is called the horizon problem. It's a physical problem. It's something that you cannot just say, well, I cure it with some dirty mathematics. It's a physical problem that you have to find a solution for. And this solution will be called inflation. Okay, so this will be the subject of tomorrow's lecture. Tomorrow what I want to do is I want to start from this picture and try to understand what we have to change in the assumption that we made so far in order to solve this problem. Then we will solve the flatness problem, the entropy problem, and we will take over from there. Okay? So I think I will stop here. And I guess you take a break and we go on with the next lecture. Unless you have questions or comments or curiosities. Nothing? All right, so see you this afternoon.